Okay, 7.6 inequalities. Number 23, they give us three separate lines, inequalities. In this case, they're not equal signs, they're actually inequalities. So, but that's okay, they behave the same as lines. We just have to accommodate the inequalities, and you'll only really see the difference in some minor ways algebraically, but mostly on the graph. So getting this into y equals mx plus b, I spread these out on purpose so that it would give me some room. I want to actually move this stuff around, move the furniture, so to speak. We'll add 3/2 x to both sides of the equation, so this cancels out. Negative 3/2 and a positive 3/2 is just gone. And the positive 3/2 also appears over here, so we end up with y less than or equal to, and I'm going to get this in mx plus b format by switching places. And that's perfectly legal because, you know, 2 plus 3 is the same as 3 plus 2. We can switch places with it. So 3/2 x. That's the benefit of switching places, is now we have y equals mx plus b, so we can graph it. And we could go ahead and do that right now if I drag this over. Plus 3 is our y-intercept. Make sure that the camera's picking that up. Yep, you can see the graph. So 3 is our y-intercept, and now we have the slope is rise over run. We rise 3 and run 2, so rise 3 and run 2, and that is our line, which obviously continues to rise and run the same amount in a straight line. In this case, I suppose we're going a -2 and then running a -2 and rising a -3. Which of course is the same as rising 3. In other words, I've gone over this with my students. You rise 3, run 2. That's the same as running a -2 and rising a running a -2 and rising a -3. Excuse me. So you keep repeating, and it builds your line. And in this case, y is less than or equal to that line. So it is equal to that line. So we want a solid line. But y is less than that, so we need to actually shade everything below that line. And this is where I get to waste a lot of my marker. So I shade everything below that line. And that is the region. Of course, my marker stops here, but the region actually is shaded forever, and the line goes off forever too. That's the whole region defined by that line. So now let's work out this one. And I would just want to get this x value over there, so y is by itself, so we can have it in y equals mx plus b format. So I'm going to subtract 1/4 x from both sides. 1/4 x. This positive 1/4 x and the negative cancel, and that leaves us with y greater than, and I'm going to switch places with these two just like I did on the previous line, so that I can get it in y equals mx plus b format. So now, -1/2 is our y-intercept, -1/2, which would be right there, and we've got to rise, excuse me, we got to rise a -1, let's put that negative on top. Rise a -1 and run a +4, which I explain to my students, of course, that that's the same as rising a +1 and running a -4, which is what I was kind of alluding to and stumbling over my words about before. So rise a -1, run +4, rise a -1 from here, gets us right there, and run a +4. 1, 2, 3, 4. So from there we would do it again, rise a -1 and run +4. And so we get a line passing through those dots. And just like I was saying, if you rise a -1 and run a +4, that's the same as running a -4 and rising a +1. It still keeps you on that same line. That's what I was trying to allude to. It's a conversation I had with all my students in the past, just trying to refresh your memory if it's been a while. Just putting the negative up here and the positive down there, it gives you the same line as if you put positive here and negative there, as long as one of these gets the negative sign and not both of them, because if you gave both of them a negative sign, it actually wouldn't have been a negative 1/4 at all, because a negative and a negative makes a positive. I probably shouldn't even elaborate on that, because my students are definitely expected to be done coming to grips with that concept. So y is greater than that stuff, that line. So y is greater than, it doesn't include that line, so it's a dotted line. The line itself is not part of the solution. And let me refresh my memory. Y is greater than. So now I have to shade everything above. Okay, so now the doubly shaded region is really the solution for both of these regions that are shaded. This region satisfies that line that we first did. This region definitely satisfies it all the way up to here. And this region, which of course goes off into infinity, this all satisfies the inequality that we just graphed. But the only area that satisfies both of them is the doubly shaded area, which actually goes off in that direction forever. But we're not done. We actually have one more inequality to combine with that, and here it is. So let's do the same thing. Let's get y by itself, minus 4x. Move the furniture, so to speak, I like to call it lately. Y is less than, and I'm going to switch places with these so it's in y equals mx plus b format. So, in this case, it's a negative 4 over a positive 1. Likewise, we could make it a positive 4 over a negative 1. That's still negative 4. But let's rise a negative 4 and run 1 from the y-intercept of 2. So the y-intercept is 2, right there. And we rise, let me refresh my memory, rise a negative 4 and run 1. So rise a negative 4, that gets us down here, and run 1. Rise a negative 4, run 1. Rise a negative 4, run 1. In other words, rise a negative 1 and run 4, or excuse me, run a negative 1 and rise 4, run a negative 1 and rise 4. We keep doing that, and we can certainly plot out as many of these points as we want following that same example. And y is less than that line. So if the line is tilted slightly to the left there, and it's not equal to, it doesn't say y is less than or equal to, it says less than, so that means any point that's actually on the line is not included as part of the solution. So y is less than, this is leaning slightly that way, so it's everything down beneath that line, which appears to be to the left, but it's really beneath it. And now if we shade everything over here, we're going to see that the only area that actually is already double shaded, I didn't really shade all the way up to the line here, is this little triangular area. So I guess I could go ahead and lightly shade everything in this direction. Because it's definitely shaded. But the triply shaded, the only region that satisfies, as I said earlier, that this is the slice that is doubly shaded, but now we've added to it this line, which is shaded this way. The only region, the only area that is triple shaded is that little triangular shape right in there. So, the grand finale explanation for this is if you take any points that are in this little triangular area and plug them into those equations, you will get a true statement, because these points that are bound by this region satisfy all three of those equations. To add food to that thought, this is a solid line, so we could actually pick points that are right on this line, even though they're like on the very border, the very edge of that triangular region. Any point that's actually on this line would still satisfy all three. If we picked one that was on this one, though, because this one's dotted, it would actually be considered out of bounds. It wouldn't satisfy. It would satisfy one of them, this one, where we shaded this way, because, you know, by being in this shaded region, it certainly would satisfy that region, but anyways, I'm just trying to add more depth to the fact that one line is solid and the other two are dotted. All that really means is that if you're right on a dotted line, it doesn't satisfy that particular line. But the only points that satisfy all three come from right inside that region, and that's the real concept that they're trying to drive home here.